Thank you very much. Very happy to be here this afternoon to talk to you about the journey that we started about 2 years ago. Wait, we've got something important.
From the men's restroom, there is an elite Marriott reward room key. It's up here.
If we were taking questions, best question would get the room key. So let me start out, since this is a case study in scalability, talking about what I mean by scalability. We'll see if the projector comes back. We'll see if we can get technical support here. You're missing an incredible cartoon. So I looked at what this scale means, and it was the number 6 question as to the smart questions to ask in any meeting that you're possibly ever in, because no one really knows what scalability is, and it drives engineers crazy. So when I talk about scalability for the next 25 minutes here, I'm going to be talking to you about the time, the breadth, and the research leverage that we've been able to get at Montana State University. And I'm hoping that Greg or Jonathan is getting the other Jonathan to get the projector back for us here. So what I want to talk to you today about is what Montana State's done with our research network. While investing in research networking makes sense for a CIO. And then I want to walk you through with our Converge network some of the scalability benefits that we've seen in software-defined networking supported by Cisco in their software-defined access. So that's what we'll be talking about for the next few minutes here. Let me level set by talking a little bit about what Montana State is. A year ago, I talked about us as a lean CI approach, meaning that we don't have a great deal of resources that are focused on cyber infrastructure. Just again, to give you an idea of the size of campus, we're about 16,703 students, 1,300 faculty, 2,016 staff. The core information technology budget for the unit that I look over is $14 million, 75 FTE. Research cyber infrastructure staff, sort of like what it was last year. We have 2, we lost 1, we got 1 back, so we're back at 2. The networking staff is relatively small, 3 FTE for the 40,000 devices that are supported on campus. And then over the course of the last year, we've added a redundant east-west 100 gigabit route for campus, and we've done that through our partnership with the Pacific Northwest Gigapop. Let me share with you sort of where we were and then how we've moved forward. I'm going to unplug just for one more second because the graphs get important. Let me talk about what the network is that we've put in place through our CC Star award. So the important thing to remember about the approach that we had to networking with the funding that we received from the National Science Foundation now 3 years ago is that we put into a purpose network for science infrastructure. So we took that question about where you take the DMZ and we moved it into 7 different buildings on campus. And those 7 buildings on campus allowed us to have floors of research-intensive data scientists that we could work with. So the physical network was where we went 3 years ago. That causes a challenge for those of us who, in the day jobs, end up being chief information officers and vice presidents for research, and that is when you have a physical research network and an enterprise network, they advance at different speeds and time. So you basically have a leapfrog problem where one of your networks is going to lag behind the other. And I would pose as a question that I think many of us probably need to think about, what happens with those 2012 CC Star awards? So they're roughly 6 years old now. All of them were supposed to transition to being taken care of by someone else, likely the chief information officer and the central IT organization, but there's no new funding. Again, you've heard from colleagues throughout the day that what we've gradually seen is reduction in funding across the board for states, which means that tighter budgets still have this challenge. So one of the questions for us as we looked at having 2 separate physical networks is 2 is always worse than 1 when it comes to funding. And that's something that we were profoundly concerned about as a sustainability challenge. And again, I think it's something that the community also needs to and is appropriately worried about right now. So we talked last year at this event about a partnership that we had with Cisco, and I will talk exclusively about Cisco. We've been using their software-defined access, which is their approach to software-defined networking. But I'll argue that in a converged world, we're going to see more and more vendor-supported enterprise solutions that are going to support SDN in a way that will have a vendor standing behind it. So what we started doing last year was looking at our physical network that supports research networking to see if we could get similar or superior performance with a converged network that would basically allow for the software to segment the research networks in the way that would move us forward. And basically, the big change for us is that we have new edge devices. The original Bridger network had Cisco 2960s. We now have 9300s that we're deploying, and we've upgraded the links from the core to the distribution layer. We also conveniently, and again, this happens sometimes when the network gods smile on you, we're at a point right now where about 33% of our access layer is needing to be replaced. So we've taken what we've seen right now in the convergence of the networks, and we've moved it into our methodology as we're looking at the access layer. So we'll be, over the course of the next year, replacing 33% of the access layer with new software-defined access switches. So I grew up in the Midwest, and my grandfather was someone who field trialed dogs. And if you don't know what that means, you put a dog in the field, they search for a bird. When they go on point, you know that that's where the bird is. My grandfather had a dog, Judicious Jake, in 1972-73, which was Dog of the Year. And I would argue that if we look right now at research networks are actually the bird dogs for what we need to be thinking about in enterprise networks. And the reason that that is important is they're giving us the ability to have the next penetration of the network that we're going to need as we think about the challenges that are going to come from ERPs to instruction. So we know from software-defined networks that we're seeing that baked in by vendors right now. We know that the flexibility that we're seeing will give us benefit not just for those research needs, but also for things that may get into segmentations necessary for voice over IP, video necessary for instruction. The other thing that we've seen in the research networking community is that we've got persistent networking tools, Mad Dash, Grid FTP, and they're giving us better persistent views of the network, which again, if you look at CIO conversations, about 70% of us think that everything is going to move more to the cloud. So research networking gives us the penetration into doing with that. We also have software tools like Globus that have been built for large file transfers, which at some point are going to be student information data. They're going to be grades. Those sort of things are going to come more into what we need, and then we'll end up with interoperable networks that are going to become more important again as all of our data, not just research data, gets larger. And I would remind you that research networking has always had a profound impact in the United States. While I know that this crowd knows this story, it's important to remember that NSFNet was just a research network. And so everything that we're talking about right now, and the conversation that Larry gave us earlier this morning about this moment of inflection that we're at, is really about the fact that research networking can and is right now having a profound national impact. So you'll have to trust me, but I will make the slides available afterwards. So the first thing that we did was look to see if a converged software-defined network using software-defined access from Cisco could get the same sort of performance that we had gotten out of our high-performance research network, which is that physically different network. We tested this with PerfSonar, got a variance in terms of our Bridger responses, but out of a 10 gig link, we were about able to get 8.6 gigs of traffic out of that. The converged SDA side was at about 9.1 with very little variance. And we think the reason that the variance decreased was, again, you're looking at about a half-life cycle of technology difference. So the high-performance Bridger research network actually is a little older. The new converged network, new technologies, giving us a little less variance. But the first thing that we proved was, sure, if you look at it, the software-defined access can perform as well as a physically separate network. And we'll have a paper that we'll be talking about more tomorrow when we do our research deep dive at 12:30 that will get into this. But the first thing is performance is as good. So let me talk about some of the use cases that approach scalability for us. And the first one of these is something that I would refer to as the dreaded unpatchable control plane. So In all research universities, certainly in R1s and also the R2s, we have core facilities. Those core facilities tend to have really great instruments that seem to have people who create them in the first place who know very little about computers or how to keep computers up to date. So what ends up happening is you get something like a very expensive electron microscope, and then out of that very expensive electron microscope, at the end of the day, you end up having an XP machine that can no longer be patched, which is the way that you have to operate this. And the classic way that universities approach this problem is really in two different ways. And we have a facility here that's called ICAL, the Imaging and Chemical Analysis Lab, that does have an electron microscope that runs on XP. The two ways that universities approach this problem, the first is to say, well, just air gap the device, so effectively take it off the network. No one needs to be able to move data off of this. That usually doesn't lead to good conversations when you're talking with researchers on a campus who need to get back to that data. So when you tell them that the network is actually an obstacle and that what they should do is get a USB drive, you're usually not leading to a productive engagement. And I would say, to give you an idea of how severe this problem is, Indiana University 2 years ago in New Mexico talked about the fact that they had this problem in a biocontainment facility, and they were taking USB drives out, bleaching them as they went into the outside world. So big problem for universities. So because you can't probably air gap everything, what you end up doing is bringing in yet another firewall. And the firewall is usually not enterprise quality because there's not enough money to buy that. And you sub-segment the network with that device. And I think we keep finding more of these, but right now there are at least 3 firewalls that at some point someone put in the network to get that segmentation that we weren't aware of. So our real question was, what can we do in a converged network that might deal with this? So we took 2 approaches. One of them was to say, how fast could we do this in the research network, the Bridger network, which was a physical network? And for segmentation, it took us about 12 hours. Took us about 52 hours worth of labor in order to get this done. And the problem is, when you only have 3 networking staff, 52 hours worth of research time actually ends up, from a labor perspective, taking a number of months. So we actually measured this out, and for us to do that work in the physically separate network, it took us 8 months to get in the 52 hours worth of work that was necessary to set up the segmentation. When we looked at this in terms of the software environment with software-defined access, we were able to do software-defined access labor segmentation in only 12 hours, and that meant that we were able to get it done in basically 3 weeks. So 3 weeks to 8 months, that was the difference in how quickly, without having to touch physical hardware, we could make things change. The second use case we had was one that I would refer to as the case of the traveling research lab. So we had a researcher, Ben Poulter, who had joined the university, had a lab over in the facility that's just to the east of this building called AJM, and that's where his lab was. So when we built the Bridger Research Network, we went into his laboratory and provided him with a 10 gig connection because he was a climate scientist. He was actually the reason that we first developed our DMZ. Well, lo and behold, Ben decided after about 2.5 years that he had a great opportunity to go to the University of Maryland and join NASA as one of their climate scientists. So Ben left the university, the lab was still in AJM, and we assumed that given that we had put a physical infrastructure into the room, everyone would recognize it and it would stay that way. Ended up happening, as those of you who are familiar with university space conversations might know, that things dramatically sort of changed, and a new department head needed an office, a new department head who was not computationally intensive. And so they put the new office over in the building that had the 10 gig connection. So our 10 gig connection was physically separate. It had become an orphan connection. The researchers in Ben's research lab, his students actually stayed here. They moved to another building. And so again, we wanted to see from a time to execution standpoint what we could do in terms of moving the lab for the researcher. So in the case of the physically separate network, it took us about 35, we'll see if another connector works better. Again, I'm back to almost the Colorado School of Mimes here, but not exactly yet as bad. So in terms of the Bridger network, it took us about 35 hours to do that work and took us about 4 months to do that. With the software-defined access, we were able to do it in 10 hours and again, only about a week of time. So scalability much quicker for us in order to resolve these issues. The reason that this matters is, in all reality, if you can't solve a researcher's problem probably within a month, you can't really solve a researcher's problem. No one has attention that they can give us for things that are going to take 4 to 5 times as long as they might reasonably expect it. The other thing that we've seen as we've been looking at the network, and this is something that surprises us, we're assuming that it's because of the change in the nature of the hardware and it being updated, but one of the challenges that we had was limitations in our physical infrastructure. So we had Cat6 in a number of buildings, and the question was what that was going to give us. And essentially the difference between Bridger and software-defined access is that with Bridger, we were able to get about 2.5 gigs out of a 10 gig connection because of the distance. And with the new technology that we put in place with the 9300s, we were able to get 10 gigs without changing anything in the physical infrastructure. So the routing hardware gave us an advantage, again, making the infrastructure that we already had in the wall more scalable, sort of a surprise as we move forward. One of the other things that's very nice about software-defined access and the DNA center that Cisco has right now that we've deployed is that it allows us to see quickly into the network at multiple different layers from access to distribution level. So one of the challenges that we have right now is in the physical network. If there's a problem along that path, we have to go grab logs, then we have to take the logs into something like Splunk, then we have to look for the thing that we think is the problem. One of the benefits, and we'll be demonstrating this tomorrow during the deep dive of DNA, is DNA actually allows us to see all of that in more or less probably 1 or 2 control planes. And interestingly, because of the network traffic that Cisco has been looking at in enterprises and campus, it will actually auto-suggest to you if there's a problem, things that you ought to look at. So scalability, again, in terms of time, is us being able to quickly see problems, not having to wait for a researcher to tell us that they've had a problem. I also want to talk about some of the things that we've been able to do in terms of our partners and collaborations. And this gets back to being able to scale beyond the campus in terms of the ability to help researchers increase their impact. So we had a researcher that we were working with, Theo Lipfert. He was one of our science drivers. He's over in the School of Film and Photography. They had developed a resource called Life on Terra that were basically video podcasts that were focused on science outreach. And we have been working with them to use the Bridger physical network to do this distribution. So what we were able to do with our partners in collaboration is start having conversations regarding what would occur if we were able to use different technologies to help move things forward. And as we started talking with Theo, one of the questions that we asked him was, do you have other needs right now outside of Life on Terra? Is there other digital content that you're dealing with? And one of the stories that Theo told us was that he had been working with a NSF Early Career Award winner over in the School of Physics who had created a video for planetariums called Einstein's Gravity Playlist. And we started asking Theo how it was that that was distributed among his film community, and the answer was on disk drives. So we asked Theo if he would be open to using a different technology to sort of prove out that you could digitally move planetarium films and reconstruct them. And we used our partners in the PRP, in particular the University of Illinois at Chicago, to prove that we could do this with Adler Planetarium. So we shipped the Gravity Playlist to UIC. Because connections aren't great from planetariums, they actually air-gapped it back to them, took the digital data to them, and out of that digital data transformation, we were able to make Theo comfortable that actually something different could be done with his data than just moving it on disk drives. He came back once he had that comfort level, and he was quickly able to talk to his other colleagues. And so we saw, as one of the surprising drivers of our research network, all sorts of digital astronomy content from Einstein's Gravity Playlist go to Central America, to go other places in the United States. So we greatly had an increase in reach because, again, of our PRP partnerships. The other thing that we've been able to do through the PRP partnerships is get access to national resources. And again, you heard the EPSCoR panel talk about the fact that we're all resource constrained, and that makes it very difficult at times to figure out how we can invest in ways that will allow us to get the impact that our faculty need. One of the challenges at Montana State University is dealing with the storage needs. So of all of our science drivers, most of them have RAIDs in their offices because we don't have the resources to provide a general data store, and most of that data isn't backed up. So we reached out to the national community and asked if there was anyone who was willing to take their national infrastructure and provide an on-ramp and an off-ramp for it out of this fabric that we're referring to as the NRP. We are very lucky that Dan Stanzione and TAC were willing to engage with us. And so with our 7 science drivers, we took all of their data, moved it from DTN to DTN here to TAC, and then to local area to their storage in Corral 3. So Dan is the first partner that we've had who's willing to sort of put a persistent resource available for the national community using DTNs as a way to move that data. And again, I would argue if I can do it for research data, I can also do it for enterprise data, and that would begin to solve some of the challenges that we have for storing data. So this is just a teaser, and a great thing that I had no slides to actually ruin any of the teas for tomorrow. We'll be doing a deep dive from 12:30 to 2 tomorrow, talking about software-defined access. So Cisco will give an overview of their roadmap. We'll talk more about why we chose it, and then we'll actually do a hands-on demonstration over on the other side of our ballrooms, where we will walk you through a network segmentation use case, a mobility and identity performance, and also moving the lab. So we'll show you the DNA interface, we'll show you what it's like to move the groups in, but at the end of the day, probably the most important takeaway, if you sit back and think about this from a vice president or a CIO perspective, research networking doesn't need to be your enemy. You can use it as a driver of the performance that you're going to need in the enterprise network. And again, we're seeing vendors collaborate in such a way with some of the open source things that have been developed in our community that they're now becoming vendor supported. We can get the performance we need, and we can get out of having to have this network or that network, have one network that we make do what it wants with software. So I'll be available at the Museum of the Rockies tonight to answer any questions about this. I will make available my slides. I swear I actually had some, and they have pictures on them. And so we'll share them post-event also. And again, we'll be sharing more data tomorrow on the actual performance in terms of the graphs of the network and latency and other things. Thank you very much.